Okay, so this is a video lesson that's going to be for the 15th of October on Wednesday. I'm not able to be in school today, and so in lieu of that, I'm at a regional student council meeting. What I'm doing here is I'm posting a YouTube video on the topic we want to learn about, which is Arithmetic Series. Just a couple of housekeeping items just before I start, just a quick reminder for everybody. A couple of you are still needing to finish your unit test from last week. If that's you, the deadline we said was you have to finish it by Friday. Okay. To some degree, you need to make sure that we're on top of that because it was supposed to be done last week. I get that you might need more time. I'm fine with that, but you need to find that time. That's part of being responsible, is making sure that you can find the time to do that. So whether that's at lunchtime or if you have like a second period spare, you can work on that. But if you're not done that unit test, make sure it gets finished. Okay. Another quick thought here. Make sure that you finish assignments on time. I mentioned yesterday that I was a little disappointed that I only had a few of them handed in. Please make sure they're getting finished on time because it's going to start negatively impacting marks, and report cards are coming due soon. So I will accept your assignments. I said yesterday morning, I said yesterday that I'd accept them up until Wednesday morning. I will even take them by the end of this class here, just because I'm coming back to the school after my meeting in Claresholm. But that's it. I need what you have done. Okay, so make sure those get finished. Okay. Today's topic is on arithmetic series. But before I do that, I'd like to start with 3 review questions of what we did yesterday. But before we even get to what we did yesterday, I want to review yesterday's concepts. One of the main things I wanted to talk with you about was patterns. And if I just go back in some of the slides that we have here, these are from last day. Hopefully one of the things that you got from yesterday's lesson is that patterns are found all over the place. Nature is a great example of where we can find patterns. Just like the spirals that you might find inside, this looks like some sort of flower or acorn. Or on this example here, the way that a tree grows is actually according to how the Fibonacci series works. So where it goes like 1, then 1, 1, then 2, 3, 5, 8. Where to find any two numbers, you add the previous two. So 5 and 8 would then give you 13, and 8 and 13 would give you 21. Another example I had here was of a seashell, which has a spiral pattern, which is quite similar to the spiral patterns that I showed you back here, like ones like this. So in order to solve patterns, you have to have good logical reasoning skills. You have to be able to figure out like how the pattern is working. So we did some examples of that with just basic number patterns. And the 2 main types of patterns I need you to know are arithmetic, which is where you add numbers. Like in this pattern here, we're adding 1, or we're adding 2, or we're adding 3. Or you can multiply by 3, or multiply by 2. Okay, so arithmetic means to add, and geometric means to multiply. You could also actually subtract. That would also be valid. And the opposite of subtracting would be to divide. So, other review from last day. In terms of solving questions, there's a couple of formulas I need you to know. Here's one of them. I pulled this slide off the internet. It uses similar terminology, but it's different than what might be on your formula sheet. I often like to change it to Tn equals Tn equals T1 plus n minus 1 d. So Tn would stand for like the last term in the sequence, the one you're looking for. T1 would be the first term. N is how many terms you're looking for, so like 10 terms in. And d is the common difference. For example, in this example here, the common difference would be going up by 2, going up by 2, going up by 2. So that's one formula you could use. If you haven't printed off a formula sheet, I really recommend you do that. It's a month and a half into the year, and if you haven't gotten on that yet, you should, not only because you're going to need these formulas now for this unit, but also because whatever you write on that formula sheet, I'm going to let you bring into a test or a quiz. So that would have been a good idea for the previous unit if you hadn't been on top of that. Another thing we talked about was a geometric series, and again, I pulled this off the internet, but the formula we often use is very similar. It's Tn equals T1 times r to the n minus 1. The idea here being that you need to have a ratio that you multiply by. So the ratio is like a 2 or a 3 or a 4 because you're doubling, tripling, or quadrupling what you have. We did some basic problems on that. So what I'd like to do to start class then is I've got 3 questions to begin with here. I'd like you to pause this video and take a few minutes of your own time to try to solve them before I actually get to the solution. We have the skills to solve these, at least I hope you do. I'd rather that rather than you just watch me solve them, that you try them yourself first. So pause the video, and then when you're ready to unpause it, and I'll show you at least one way of solving them. Okay, well, hopefully you paused the video here. The first question here, I mentioned last day, everything we're going to solve from now on is going to be a word problem. That's kind of a reality of where math is going. We spent a huge unit working on algebra skills to hopefully work on those. But now we actually have to do something with math. Math can't always just be X's and Y's the whole time. It actually has to have some context. So just so you know, in this unit, every question will be a word problem. So I'm going to recommend that when you solve a word problem like this, that one of the places you start is by making a bit of a table of values. It's a good way of organizing your work. I'm not going to be able to accept work that is messy and all over the place and crazy anymore. I need it to be organized and logical. That's what consists of good math. It has to be followable. So the reason why I want to make a table of values is to keep track here. So it says that he jogs for 12 minutes each day for the first week. So it might make sense to then say in week number 1, he jogs for 12 minutes. And then according to the pattern, he does a 6-minute increase each week after that. So in week 2, going up by 6 minutes makes that guy 18. And in week 3, going up by 6 minutes should make that 24. Now, this works. Like, we can keep the table of values going and eventually figure out what happens until we get to 60 minutes. Because that's ultimately my question is, when will you get to 60 minutes? So we're not sure what week it'll be. You could make a long table of values, but I'm not looking for that anymore. I'm looking for you to algebraically prove where this comes from. So one of the ways that I'm hoping you might be able to solve this, if you didn't already, is to use a formula. And hopefully the first thing you'll recognize is that there's one of 2 formulas to use. It's either this formula here, or it's this formula here. It's going to be your job to figure out which formula fits best. And that's going to be a big part of where we go in math is, I won't always tell you, you've got to figure that out yourself. This first formula is if it's arithmetic, and the second formula is if it's geometric. So the first question you have to ask yourself is this pattern going up by a common difference or by a common ratio? So a difference means you're adding a number, a ratio means you're timesing by a number. So hopefully it already makes sense to you. You're going up by a common difference. So we need this formula. Tn equals T1 plus n minus 1 d. Let's fill in what we know then. Tn is kind of like our last term. We know that eventually you're going to be running 60 minutes in a day. We also know that you started with 12 minutes in a day. But we don't know n. We don't know how long it's going to take to get there. But lastly, we do know the common difference. We know we're going up by 6. This is what I'm expecting, by the way. I don't really want to see a table of values anymore. You could keep this table going and go 4 gives you 30, and 5 gives you 36. But I'm looking for this from now on. I'd like to actually see some sort of proof. You know, like not just a guess and check, or a keep the table of values going, but actually show me why the answer is what it is. To solve this then, we need to use our algebra skills. So to get n by itself, n is the number of the number of weeks it's been, we'll have to subtract 12 from both sides. So that means you've got 48 equals n minus 1 times 6. We'll have to divide by 6. 48 divided by 6, that 8? I think that's 8. 6 times 8 is 48. And then we need to add 1. And based on that, it should take 9 weeks for this guy to eventually have run 60 minutes. So like if you kept this table going, eventually 60 minutes would happen on week 9. And if you want to, you could keep this table going, but that's kind of the point. I don't want you making a table of values every time. I just want you to kind of get started with it. So Hopefully that one makes sense. If something doesn't make sense, two thoughts here. Make sure that you rewind the video and rewatch it. And if you have questions, make sure you make a note of it. If I make a mistake by some chance, like I can't do basic math, make sure you make a note of it, and we can talk about it on Thursday when I'm back. So, here's the first question. Well, let's look at the second question. A hot tub is not considered hot enough, so the temperature gets raised. It gets raised by 10% each half hour. That's a key thing there, half hour. After 3 hours, what the temperature of the hot tub is. So, I might recommend then that a good place to start would be to make a table of values. So I might have like the, I could have like say the time, and I'm going to do time in like half hour increments. And then the other thing I want to do is I want to know what the temperature of the tub is. So when we start with time 0 then. What is the what's the temperature when we start? And I'd say, well, the temperature when we start is 75 Fahrenheit. Now here's where this gets kind of tricky. We need to keep track of some math. I'm going to throw a calculator up on the screen just to work with as well. So I'll put the calculator over here. Let's move this guy over here. Hopefully that still works. Should still be able to see that. Now it goes up by 10% each half hour. So if you were to do 75 and times by 10%, the temperature went up by 7.5 degrees. So if you were to add the 7.5 degrees to the 775 that you had already, after 1 half hour, now keep in mind, this time right here is not in hours, it's in half hours. So after 1 half hour, the temperature is now at 82.5. Well, after 2 half hours, I should make a little note here. 2 half hours. Yeah, that doesn't really make sense like there. 2 half hours. This right here is actually 1 hour. Hopefully that makes sense. 1 hour is equal to 2 half hours. So this is when we started. This is after 1 half hour. This is after 2 half hours, so this is actually 1 hour. 3, 4 would be 2 hours. 5, 6 would actually be the 3 hour mark. Does that make sense? It's going to be really important to like keep track of things like this. So this would be before I even start, after 1 half hour, after 1 hour, after 2 hours, after 3 hours. Okay, well, to figure out the temperature after an hour, we don't add another 7.5 because it increases by 10%. So 82.5 times by 10% means that in this half hour, it actually goes up by 8.25. So when I add 8.25 back to 82.5, this guy right here is now up to 90.75. And the difference, it's actually not a common difference, it's a common ratio. Now, one of the best ways to find a common ratio then, which we learned yesterday, is to take two consecutive numbers and divide them. So if you took 90.75 and divided by 82.5, you'd get 1.1. And if you were to try that again by taking 82.5 and divided by 75, you'd also get 1.1, which is good because the ratio should be the same. The reason why it's 1.1 is that it's almost like it's 1.10. You get to keep 100% of what you have and add on 10% more. Now, we could keep this pattern going by hand, but I'd much rather use the formula. So the formula for this, I'm just going to write this over here. Your ratio was 1.10. That kind of went off the screen there. Just bring that back like this. Hopefully you can see again here. So the formula we need then for a, not arithmetic, but a geometric sequence is this. To find any term, you need to know the first term. You have to times by the ratio to the n minus 1. So our first term, this is where things get a little confusing. You got to really watch the language right here. our first term is not 75. Our first term is actually 82.1. Term 1, after 1/2 hour, it's been 82.5. That's so important. I want to say that again. The initial term is actually not this 75 right here. Really, the first time that we've actually started, I would say that T1 is 82.5. Okay. Our ratio we just solved, we're going up by 10%, so that's 1.10. And the way it's been phrased here is we're looking for after 3 hours. So I just want to make sure we're clear. Like, this is after no hours, after 1 hour, after 2 hours, after 3 hours. So we're actually looking for 6 half-hour increments to go for. So it'd be 1.10 times 6 minus 1, which could be 82.5 times 1.10 to the 5. So to solve this, it'll look like this. You'll have 82.5 times 1.10 to the power of 5. And I get an answer of, keep losing this here between screens, 132.867. For those of you guys in my physics class, we do use sig digs. I don't really care about that in math class right here. We're not really doing it like that. So if you round it to something reasonable like that, that should work. There are some other ways of solving this, but I definitely am going to want to see a formula like this nearby. Okay. What I don't want to see is a solution that just consists of you keep randomly putting numbers in a table of values, because that doesn't really show me how you got those values. That's just you keeping the pattern going. I'm actually going to want to see one of these formulas. So again, if I have questions on that one, pause this, rewatch. Really key step here is that our T1 was this 82.5 right here. That was really important to keep track of that, because if you started with 75 and went 6 minus 1, you wouldn't have got the same answer. Okay, last question involves a post being driven into the ground. And so once again, I'm going to recommend start with a table of values. And so basically the best way of describing this would be like what strike number he's on. And then this would be how far the spike can go on the ground. And I hope this makes sense, that as you try to drive a spike into the ground, it gets harder and harder to hit into the ground. And eventually what should happen is that you can't actually drive it into the ground at all, because, I mean, it's all the way into the ground, or it's just you're so deep into the ground it's difficult to make it go further, right? So for example, on the first strike it goes in 30 inches. On the second one it's 27 inches. The third one, if it's arithmetic, should be 24. Then the fourth one is 21, and so on. So one of my questions is, what is the total distance the post can be driven into the ground? First thing we're going to have to do is figure out when will the spike stop moving. And so like on what strike number will the spike no longer go in the ground, mainly because the spike is probably all the way into the ground. So I'm actually going to solve for when the spike has a value of 0 and figure out like what strike number it happens to be. I want to just add that extra question in here. I might ask you like, how many strikes will this take? So to solve that then, if it's arithmetic, you use the formula Tn equals T1 plus n minus 1d. To solve this, Tn is going to be like the last number we're looking for. So I don't know how many strikes it's going to take. That's this n right here. But I do know when I'm done, that value is going to be equal to 0. The first value is 30. We don't know what n is. Here's a trick question here. D, the difference, it's not 3. It's negative 3 because it's going down by 3 every time. So how do I solve a question like this for n? Well, I'll start by minusing 30 from both sides. So minus 30 equals n minus 1 times by minus 3. Hopefully it makes sense why it had to be a negative 3. You're then going to divide by negative 3 to give you 10 equals n minus 1. Add 1 to both sides. It's going to take you 11 hits to get it into the ground. Well, actually, I think it's going to take you 10 hits to get you into the ground. So 1 hit for 30, 2 for 27, 3 for 24, 10 for 21. Hit number 11, the spike is in the ground. So I guess it takes you 10 hits because this one's probably 3 and 9 is probably 6 and so on. Okay. Here's where this leads into today's lesson then. In order to figure out the total distance the spike has been hit into the ground, we then would need to take 30, add it to 27, add to 24, add to 21, add to 18, add 15, add 12, add 9, add 6, and add 3, and that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 strikes that you hit it into the ground for. My hope today, though, is that rather than having you guys add up all these numbers in this pretty unorganized manner that I'm doing it right here, there's actually a formula that can make it work better for us. So I'll leave this question right here. We're going to come back and solve it a bit later with the formula that we're going to solve for. So hopefully that made sense so far. If not, like I said, rewind and ask questions later. So to solve a question like that, I want to introduce a concept here. Let's say I asked you to add all of the numbers from 1 to 10. Here's how that might look. 1 plus 2 plus 3 plus 10. If you did it on your calculator, oops, don't want an Internet Explorer. I want a calculator. Hopefully it would look like this. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. And I hope you'd agree that this is really tedious. It's really long to add them all up to get that it's equal to 55. So I'm trying to make a point here. I'm trying to show you there's a faster way. If you were to add 2 plus 3 plus 4 all the way up to 11, hopefully this makes sense here. 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11, you discover, oops, didn't press enter. You discover the answer is 65. Hopefully you can get that yourself. One way of looking at this then is that from 1 to 10 involves almost all of the same numbers as from 1 to 11, with one difference. There used to be a 1 on the front that you've now taken off. So that would be like subtracting 1 from 55 would actually now make it 54. But then the new number that's on the end now is 11. So that would actually mean, well, add 1, like the 1 that you took off right here, add that 1, and also add 10 more. Hopefully that makes sense. From 1 to 10, if you wanted to add 11 and take this number off the back, then really this 1 and this 1 right here cancel, and you're actually going to be adding 10. Which means that if I were to add the numbers from 3 to 12 real quick, it's actually going to be 75. Because I'm going to pull off a 2, which means the number is going to be 2 less. Then I'm going to add a 12, which means it's going to be 2 more plus 10 more. The idea I want to go here is that there's actually a faster way to start adding some of these numbers. Because let's say I wanted you to add everything from 1 to 1,000 or from 500 to 50,000. That's ridiculous. That's never going to happen. Like, that's going to take you all class. Maybe you've already started and you're going to realize like it's going to take you like 10 minutes just to add them all together. Like 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Hopefully you get the idea. It's ridiculous. So I want to present to you a faster way of adding numbers up. And that goes back to solving this question here. If you have to start adding some numbers like this, it was pretty reasonable to add up 10 numbers because it only took 10 times to hit the spike in the ground. But if we're adding more than 10 numbers, like if we're adding 1,000 numbers, we need a faster way. So I want to present to you a guy, his name was Gauss. And when he was a child, there's a story that says that his teacher actually asked him as like a punishment to add all the numbers from 1 to 100. Apparently he was a very smart child and he was driving his teacher nuts. So as like a way to get the child out of her hair, I guess, she made Gauss go like 1 plus 2 plus 3 all the way up to 100 and add them all together. Now he lived back before calculators, so the teacher figured that, well, this will take him like a solid half hour for him to solve, and then she'll have some peace and quiet for a while. According to the legend, he finished it in like 45 seconds and came back to her and said, "I've got the answer." And she was like, "This is crazy. How can this like grade 2 kid have solved this question that should take half an hour in like a minute?" So she did it herself and discovered he had the right answer. And so what I'd like to share with you is his suggestion for how to solve a problem like this. And it has, again, to do with patterns. Okay? I'd like for you to take a look at 1 plus 2 plus 3 is 6, 1 plus 2 plus 3 plus 4 is 10, and take a look at a couple of patterns that Gauss discovered. It's easier to do this with the even-numbered series. So this one, and this one are probably the easier ones to start with. 1 plus 2 plus 3 plus 4 is 10. Here's what Gauss did. 1 plus 4 is equal to 5. 2 plus 3 is also equal to 5. So 2 5s is 10. Try the same thing with this even series here. 1 and 6 is a 7. 2 and 5 is also a 7. And 3 and 4 is also a 7. So 7 and 7 and 7. 3 times 7 is 21. Same thing here. 1 and 8 is a 9. 2 and 7 is also a 9. 3 and 6 is also a 9. 4 and 5 is a 9. He now has four groups, 4 nines basically. 4 times 9 is 36. This is what Gauss discovered is a fast way of him solving a question like this. It works better with even numbers. There is a method for odd numbers, but I want to present to you basically an idea like this then. All of the numbers from 1 to 100 then have a grouping to them which add up to 101. 1 plus 100 is 101. 2 and 99 is 101. 3 and 97 or 98 is 101. 4 and 97 is 101. And in the middle, the two numbers in the middle that would add it up to 101 would be 50 and 51. Those would also add up to 101. So what he decided to do was basically say, well, how many groups of 101 would you have? Well, there'd be from 1 to 50, basically half of your numbers would have a pair on the other side that you could combine with to get to 101. Like 1 would go with 100, and 2 with 99, and 3 with 98. And so everybody up until 50 would have a pair. So what he did is he said 50 groups of 101, and then all he had to do is times those together. So 50 times 101. Oops, this isn't going to work. 50 times 101 is 50. He told his teacher he was done, and like I said, she couldn't believe him that he could possibly have solved that quickly, but she actually then went through the process of adding them all one at a time, and he was correct. Hopefully that made sense. If not, you need to rewatch that, because that's a huge key for where we're going. Because on the next slide, I want to introduce something different. What if we don't know what number we're stopping at? Like, what if we're adding 1 plus 2 plus 3 plus 4, but we don't know what number we're ending at? So this number could be 100, or this number could be 17. Okay. Well, rather than actually putting a number here, what we've done is we've said, well, this number here is n. Which means that the number before it is n, but 1 less. So like if this guy was 17, this guy is 17 minus 1 for 16. And this guy is 17 minus 2 for 15. So that's kind of a way of phrasing it. The way this would work then is you have from 1 to n, that would be an n plus 1. 2 combined with n minus 1. If you go 2 plus n minus 1, it's actually n plus 1. If you go 3 with n minus 2, it's still also n plus 1. So his group is n plus 1. And then how many of them do you have? Well, however big this number is right here, you need half of them. So that's where, like, it used to be 100 over 2 and 100 plus 1. Well, now it could be 17 over 2 and 17 plus 1. So what Gauss discovered is there's actually another formula we can use. Now, rather than using Tn, which finds you just a single term, Sn is actually the sum of adding all those terms up. So this formula is also on a formula sheet. I might have phrased it like this, though. I might have called it Sn equals n T1 plus Tn all over 2. But the basic concept is you need your first number, that's T1. You You need your last number, that's Tn. You need to know how many numbers you have, and then you got to divide it by 2. And that will add all these numbers up for you. So what I'd like to do now is invite you to go back to the first question on the previous slide, and let's try solving it. So using this formula here, let me just erase some work. You already have an answer for adding all these up, but here's a faster way. To add all your numbers, you need to know how many numbers there are. You need to know the first number. You need to know the last number. And you've got to divide by 2. So, how many numbers were there? Probably the best way of doing it is you had to hit this thing 10 times. The first time you hit it in 30. The last time you hit it, you actually hit it in 3, because like that would have been, this would have been the last one that you used. 10 with 3. And then divide by 2. So 10 divided by 2 is 5. 30 plus 3 would be 33. So then 33 times 5, 15. 3 times 5 is 15. So hopefully you got 165. And that would, in theory, be a faster way than actually adding all of these numbers up one at a time. So hopefully I didn't make a mistake there. There's one more formula that's very similar to it. This is the formula that I believe I put on your formula sheet for you. Another thing that you could do is this Tn right here, which stands for your last term, you could actually use a different formula, use a system of equations, and do substitution, and plug this stuff right here in for that Tn right there. And what you'd end up with then is you'd have an extra T1 plus n minus 1d. This T1 and this T1 would then add together, giving you this new formula, which is Sn equals n over 2, 2 T1s, n minus 1d. So in this formula, if you want to add everything up, you need to know the number of terms, you need to know the first term, you need to know the number of terms again, and you need to know the common difference, and that will add all your numbers up. So long story short, we now have 4 formulas. This is a formula, this is a formula, this formula right here is another one, and then there's also the Tn equals T1 r n minus 1. And so I need you to be able to work with at least these 4 formulas for now, and you might have noticed on your formula sheet there's even more formulas than that than we're going to get to. So having been shown that, now I want to solve some more questions. So what I'm going to do is I'm going to solve the first 3 questions together with you, and then I'm going to have you guys try to solve the last 3 questions by yourself, and we're going to try to start class tomorrow with those questions, because my runtime right now is about 33 minutes. So I don't want to make this lesson go for too long. I want it to run just under an hour, so you have some time to work on those last ones. So let me start here. The first question is a theater has 60 seats in the first row, 68 in the second row, and 76 in the third row. So let's start with the table of values. Table of values. And by the way, when you guys do an assessment, like a test or a quiz, I'm going to expect a table of values just to get started. But I don't actually want you to keep that table of values going for forever. That's not a really good, that's not a solid math way of solving things. I could give a grade 8 kid this problem, and he can make a table of values to keep going. But that's not really solid math skills, not for Dash 1. So in this column here, I might put down, like, say, what row it is. And here I might say how many seats there are. So in the first row, there's 60 seats. Second row, 68. Third row, 76. And I could keep this going, but that's not good math. My goal is, by the 20th row, I don't actually just want to know how many seats there are. I want to actually have added all of these numbers up and figure out how many total seats there are. So I have 2 basic formulas then. Let me go back a slide here. One of the formulas is, let me write them out here. Sn equals n T1 plus Tn over 2. And the other one is Sn equals n over 2. 2T1 plus n minus 1d. So my question for you now is, which of these two formulas do we have the information we need to solve? Do we know n? And the answer is yes. How many rows is there going to be? There's going to be 20. Do we know t1? Yep, we know that. There's 60 seats in row 1. That's good. Tn, though, would be how many seats there are in that 20th row. And I don't actually know how many seats there are in row 20, so this formula right here is not useful to me. This one right here is useful to me. I know n, 20 rows. I know my first row has 60 seats. I know that it's 20 rows, that hasn't changed. And my common difference between rows hopefully makes sense. Each time it's going up by 8. The key here now is to not mess up your calculations. So I'd recommend trying something like this. 20 over 2 is 10. 2 times 60 is 120. And then 20 minus 1 is 19. And you're timesing by 8. And that maybe makes more sense to put in a calculator. So 10 bracket 120 plus 19 times 8. Bracket 120 plus 19 times 8. And so this is much faster. Apparently there are 2720 seats in the theater. So hopefully that made sense to you. Let me just recap what we did there. We made a table of values to get started. I wanted to figure out row 20, but I wanted the total number of seats. So I had to use either this formula or this formula. Based on information given, it's very similar to some of you guys in my physics class. You've got to figure out which formula is useful, and I don't know Tn, because Tn would have been how many seats there were when we were done. We don't have that information yet. But I could use everything in this formula. The key then is plugging everything in. So n means there's 20 rows. T1 means that there's 60 seats in the first row. N again means 20 rows, and the difference was 8. Okay, next question. I'll try solving one for you here. Julia makes $2 in her first hour, $4 in her second hour, $6 in her third hour. How much money does she make after an 8-hour shift? Granted, this is a weird way to get paid, but let's go with it. So let's put down hour and how much money she makes in that hour. So in hour 1, $2, hour 2, $4, hour 3, $6. So like after 3 hours, she's made $2 plus $4 plus $6. So she's only made $12 after 3 hours, which is not really all that good. But it's about to get better, because in hour 4 she makes $8, and in hour 5 she makes $10. And so after a while, like, you could keep this going, but I don't want you to. But after a while she'll have worked 8 hours, and I'm going to have to add all of her money together to figure out how much she actually made total. So the two formulas we had, let me just rewrite them again, are Sn equals n over 2, what is it, Tn plus T1, and the other one is n over 2, 2Tn plus n minus 1d. Which of these formulas do we have enough stuff to solve for? For this formula, we need to know how many hours she worked. That's n, which is 8, so that's good. But Tn would be how much she earns in that 8th hour. So unless you want to actually figure out how much she earned in that 8th hour, which you could do, we could keep the pattern going. This would be 6, 7, so this would be 12, 14, 16. Okay. Well, now that I know how much she earned in that hour, I could actually use this formula. Sn equals 8 over 2, because she worked 8 hours. N is 8, divided by 2. In the 8th hour, she earned $16. In the first hour, she earned $2. So this would be 4 times 18. 4 times 18, just to make sure, would be $72. So $72 for 8 hours worth of work means it was $9 an hour on average. If we did this properly, though, we should be able to solve this using the other formula. So that would have been Sn equals n over 2, 2Tn, that's T1 actually, sorry, 2T1 plus n minus 1 d. So let's try it the other way. N is how many terms, or how many hours there were, so she worked an 8-hour shift. You got to multiply your first number twice. So in hour 1, she was only getting $2 an hour, kind of a ripoff. Again, it was still an 8-hour shift, so whatever 8 went here, 8 goes here as well. Minus 1, and then times by d. What's d in this case? Well, she went from 2 to 4 to 6 to 8, so every hour she's going up by $2. You just got to be really careful you don't screw up your math here. 8 divided by 2 is 4. 2 times 2 is 4. And then it's 7 times 2. So it's 4 times 4 plus 14, which is 4 times 18. And 4 times 18 is the $72 that we got before. So 2 different ways, both valid for solving. What I don't want to see, I won't give you full marks, I probably won't give you very many marks at all, is if you were just to write your table of values here and then tell me that adding them all up was 72. I'm expecting better than that now. For a Dash 1 math student, I'd like to see that you're actually able to prove to me why the answer is 72, not just adding all these numbers. Yes, it's possible for you to solve it on this example here, but it's not always possible for you to make a table of values this long. And I'd like to show you how that's possible on the next example. So again, if you had questions on that one, please go back and look at it again. One of the nice things about doing this video lesson is everyone can go at their own pace. If you wanted to, you could even take a break if you need to. Just take a pause for a second, make sure that it makes sense. My current run time looks like it's about 42 minutes. So my thoughts are this is probably going to take about an hour just for the lesson, let alone some work time before and afterwards. So here's my last example. An employee is offered a starting salary of $70,000 and raises of $8,000 a year. My question now is how long will it take for you to earn a total of $1 million? So let's write this out here. This would be like what year it is. And then this would be how much money you earn. Okay. In year 1, you earn $70,000. In year 2, you're up to $78,000 because you made $8,000 more. In year 3, you'd be up to $86,000, etc. Well, my question here is not what year will you earn $1 million? Because, I mean, if you're doing $70,000 with $8,000 raises, I don't want you to earn $1 million in 1 year. That's going to take you forever to get to. But at some point, if you would have taken all of these numbers and added them all up, eventually you'll have made actually $1 million total. Now, granted, in real life, you probably don't take all this money home because of like taxes. You got to spend money, obviously, like you got to live. But hopefully this makes sense as a question, like at what point in your life would you have actually earned $1 million total, before spending? So in terms of values we have then, sometimes it makes sense to write them down like this. Your first term was $70,000. Your common difference was $8,000. Do we know how many years this is going to take, though? Well, that's the point of the question. Another question, do we know how much money you'll make in that last year? And again, we don't actually know how long it'll take to make all that money. But what we do know is that the sum of all of this money is $1 million. And so what's going to happen in this example here is we're going to work backwards. I need some more room here. The formula that would then work really well for this one is this. Sn equals n over 2, 2t1s plus n minus 1 d. The reason why this formula makes a lot of sense is I have Sn. I don't have n, so I'm going to solve for n. I do have T1, and I do have D, but I don't have this n here either. So we're actually going to work backward and solve for n, and it might look like this. $1 million is equal to n over 2. 2 times our first term was 70,000 plus n, we still don't know what n is, minus 1, and then D was $8,000. So I've plugged everything into my formula, but rather than solving for Sn, I now have to solve for n. I don't know this n here or this n here. To solve this, I'm going to recommend that we kind of simplify things a little. And here's two main suggestions I'm going to have for simplifying. This 2 right here on the bottom of the fraction, the best way to get rid of it is to times it to the other side. That's one of the things we learned about in our algebra unit, is to fix a fraction, multiply the denominator to the other side. So it would make sense to say this is 2 million equals n. Now that that 2's gone, let's combine some stuff. 2 times 70,000 will be 140,000. And then again, this is why we did our algebra unit. This 80,000 needs to get FOILed. So you're going to have 80,000 n minus 80,000. If this doesn't make sense, please rewind and take a look again. This is where, you have to have a good grasp of your algebra skills. Some of you may see where this is starting to go. You then need to FOIL in this n to every term. And so what you're going to get is 140,000 n plus 8,000 n squared minus 8,000 n. I'm just going to pause here. So I'm hoping you have a bit of an aha moment. What do we have at this point? We have a quadratic, which is why we did this whole first unit first, because we need to be able to solve this quadratic. Why do we have a quadratic? Because you've got an n squared. So to solve this sort of question, combine your like terms, and let's put our 2 million on the other side. So it might look like this: 0 equals 8,000 n squared, and then 140,000 minus 8,000 should be 132,000 n, and then you're going to be subtracting that 2 million. So now we use the quadratic equation, which is ridiculous, because using the quadratic equation on a question like this is way too big. So I have another suggestion for you. All of these numbers are in terms of like how many thousands there are. So what if we divided everything by 1,000? 0 divided by 1,000 won't change. This guy will now be 8n squared. It'll be 132n. And if I take off 1,000 here, this guy will now be 2,000. It's not perfect, but it's a whole lot better than it once was. So next step, quadratic equation. Negative b plus or minus b squared minus 4ac all over 2a. One thing I should point out, math is cumulative. Cumulative as a word, if you know that word, cumulative. It means that all the skills that you've previously learned, we still need them. You can't just stop using quadratics. They don't go away. We're still going to use that. All of the algebra skills like foiling and factoring and even things that you learned in grade 1 and 2 like adding and subtracting, you still need to know all that stuff. So, using the quadratic formula then would be negative 132 plus or minus 132 squared minus 4, 8, negative 2,000, all over 2 times 8. What should happen is you're going to get two different answers. So let me try solving this here. I'm just going to simplify. A lot of you like to find what's under the square root sign. So it might look like this: negative 132 plus or minus the square root sign. It'll all be over 16, because it'll be 2 times 8. So 132 squared minus 4 times 8 times minus 2,000. Oops, too many zeros. Hopefully remember the term for this. Under the square root sign is called a discriminant. And I've got the value 81,424. Let me rewrite that. So that means we've got negative 132 plus or minus the square root of 81,424 all over 16. To solve this, we're actually going to need to put it into a decimal value. So it would look like this. Negative 132 plus the square root of 81424, close brackets, divided by 16 means that one of my answers is 9.58. But in the quadratic equation, there's always two answers. So go negative 132 minus the square root of 81424. Then divide by 16. And I got negative 26.08. We learned a term in the last unit then. It's called an extraneous answer. And it does not make sense to have a negative time value. Like, that's completely illogical. It makes total sense that after about 9.5 years, so 9.58 years, so partway through the 9th year, well, actually it's going to take 9 full years, 9.58 years basically then, right, is how long it'll take for you to hit the $1 million mark. So, I mean, sometime partway through the year, if you add this number and this number and this number and this number, 9.58, having added them all up, you'll finally hit the $1 million mark. I think that's kind of a cool question to look at there, because that could be you guys at one point in your life. You might actually have a goal of one day being a millionaire. Now, granted, you probably won't be able to save every penny you ever earn, but you could solve a question like this and figure out how long it would take for you to become a millionaire based on like your salary and annual increases and stuff like that. One of the points I want to make here then is that with these formulas I've given you, let me rewrite them one more time. There's the Sn equals n over 2 t1 plus tn. There's the Sn equals n over 2 t1s plus n minus 1 d. There's tn equals t1 plus n minus 1 d. And there's tn equals t1 times r to the n minus 1. When it comes to these formulas here, you need to know first which formula to use, and then you need to know how to rearrange it appropriately. Because I don't always ask for you to solve for something that is on like the left-hand side of the equation by itself. I could ask you to get tn by itself, or to get n by itself, or to get d by itself. And so that's what makes some of these questions more challenging. My current runtime is up to about 53 minutes, which I'm guessing is well over that for you guys. If you haven't taken a break, you may want to just pause for a second and take like a 5-minute break. Maybe just let the substitute teacher know that you're going to go grab a drink of water or something. Here's my goal for you then. There's 1, 2, 3 more questions left. I've done some examples for you guys. I want you to solve these last 3 examples, and I want to start class tomorrow with them. So hopefully you have about 15-20 minutes left in class, maybe a little bit more, maybe you have half an hour if you're a fast worker. Okay. I'd like for you to have these at least attempted. Okay. One last thought. I said this at the beginning of the lesson here. If you haven't finished your unit test, you must finish it by the end of the week, or I'm marking what you have. Okay, we have to move on at some point. Okay. Another thought, make sure you stay up to date. Some of you fell behind on your assignment. Please have it ready for me to collect by the end of today. Like, I'm coming back on the bus hopefully any minute now. I'm going to mark these tonight and give them back to you because we're done with that first unit. We need to move on. Okay. And then the last thing I want to mention is when it comes to grades, report cards are coming due soon. So we're going to have to start figuring out a mark for you. In terms of progress logs, you can omit your 2 worst grades, but that's it. You have to count everything else. So hopefully you've been doing a good job of keeping up to date and making sure that you improve and get better. The same thing will go in this unit. We're going to do a couple of quizzes, a couple of assignments, a unit test. Please be more on top of things this unit, because I've said this before, it's not going to get any easier. We're taking Dash 1 Math. It's the kind of thing where our goal is to help you get ready for university level calculus. If that's what you're hoping for, that's what I'm going to help you get ready for. If you're not looking for university level calculus, now may be the time to consider dropping down to Dash 2. Now is about as good a time as any, but I would recommend do it sooner than later. Don't wait until it's too late, because then you might not have an easy time passing Dash 2 Math. But please make sure you stay on top of things, I guess is my goal here. Don't fall behind, okay? It does not work well. You have to be a proactive, on top of things student to do well in my class. So, okay, just last reminder then, please make sure that you try these 3 examples for tomorrow, and we'll start those to start Thursday's lesson. So hopefully this lesson went well. If you need to, rewatch it at home, rewatch it later. I mean, that's the beauty of trying to record a lesson like this, is that you can watch it again and again and again as many times as you want. So I'll